Hi friends, in our last session, we have completed with advantages of geometric progression. In today's session, we are going to see preferred series. Along with that, we are going to start with the design procedure of multi-speed gearbox. This is Faizan Kagdi and I welcome you all to our lecture series of machine tool design. So let's begin. Now, preferred series. Now, usually it is used for geometric progressions. Okay, that is GP. So, in gearbox design, a set of preferred step ratio or preferred numbers is used to obtain the series of output speed of a gearbox. The preferred step ratio is mentioned as a basic series named as R5, R10, R20, R40, and R80. Each of these basic series has a specific step ratio and it is denoted by R. Now, the concept of this preferred series has been developed by Charles Renard. Okay, so this makes quite easier to determine the geometric progression ratio. Basically, we can say that whatever is a preferred series answer is our phi, that is a gear ratio. So in a data or in a numerical, it will be mentioned that we need to design a gearbox considering R20 as a preferred series, which means what? It is given as phi 20. Okay, so by using this, we can determine the geometric progression ratio or a gear ratio. Now, how we can do that? So you can see I have shown one box in which it has been given that R40. So R40 can be written as 540. So 40 is in a subscript. Okay, and it is equal to 40th root of 10. So if we find out this, it is going to come 1.06. Similarly, if it is given in a data R20, so which means it is 520. Okay, so how we can determine its value? The value of geometric progression ratio. So it is equal to 20th root of 10. Remember, we are going to find out a root of 10. Okay, so if it is 20, so we would say 20th root of 10, which would be equal to 1.12. Similarly, if it is R10, so denoted by phi 10, which would be equal to 10th root of 10, which is equal to 1.26. Similarly, you can see I have last found out phi 10 by 3. So R10 by 3 would be given, so it would be 10 by 3 root of 10 is equals to 2. Okay, so the preferred step ratio is mentioned as a basic series named as, remember, R5, R10, R20, R40 and R80. So you need to keep this in mind that this would be mentioned in a data, but you would have to find a corresponding value of this Charles Renard series. Now let's proceed further and see our next topic, that is design procedure of multi-speed gearbox. So this is the most important steps. This is also asked in the exam that in a 7-mark question, design the procedure or describe the procedure for a multi-speed gearbox. So remember the steps. Okay, and these steps we will going to use while solving the numericals. Okay, so first what we need to do, so first we need to calculate the range ratio of a spindle speeds. Now we know how we can determine that range ratio. So the range ratio formula is maximum spindle speed upon minimum spindle speed. Now for that, usually in a data, in a numerical, n max would be given and n minimum would be given. Okay, but if n max and n minimum are not given, then two values corresponding to this will be given, that is V max, cutting speed would be given and minimum diameter would be given. So it is very obvious that for a minimum diameter we have to keep the maximum spindle speed, right? That is, when a diameter of a workpiece is smaller, so we can keep maximum speed, and when a diameter is maximum, that is larger size of a workpiece, then while machining it we need to keep a smaller spindle speed, that is n minimum. Okay, so you can clearly see that if we need to find out n max, the equation is 1000 V max upon pi d min, and if we determine n mean, that is minimum spindle speed, equals to 1000 V min upon pi d max. So in usual case, always n max and n minimum will be given in a data, so you directly have to find out Rn, that is range ratio. Okay, so Rn can be found out by using this equation. Okay, now if we substitute this value of n minimum and n maximum in this equation, so what we are going to get, so we get Rn is equal to V max upon V min into D max upon D min. Now can I say that V max upon V min is a ratio? So which ratio it is? So we would say it indicates the range of cutting speed. Okay, and d max by d min indicates a range of a diameter of a workpiece. So we can write it as rb into rt. Okay, now you remember that only we are going to use this equation to determine a range ratio in numericals. Now next we need to calculate total number of spindle speed steps. So what is a spindle speed step? So it is basically the number of speeds available in a gearbox. That is, we usually say a 6-speed gearbox, 8-speed gearbox. So this 8 indicates a speed steps available. Okay, so that is denoted by Z. Remember, denoted by Z. Now what is the relation for that? So we know the equation range ratio Rn is equal to 5 raised to Z minus 1. Now we can determine Z. So for this we need to find out, we need to apply logarithm on both the side. So what we get, so we would say that whatever in a power will come in a bottom side, so it is going to become Z minus 1 log 5 to the base 10 equals to log Rn to the base 10. Now making Z minus 1 subject, so we can write it as log Rn to the base 10 upon log 5 to the base 10. Finally solving this, we get Z is equal to log Rn to the base 10 upon log 5 to the base 10 plus 1. Taking LCM in a final equation. Now you can see over here log Rn to the base 10 plus log 5 to the base 10. So can we apply a log rule, that is of addition? So the product, so it is going to convert into multiplication. So over here you can see Z is equal to log Rn into 5 to the base 10 upon log 5 to the base 10. So this is a general equation to determine a number of speed steps if in a data range ratio is given and phi is given. So by using this equation you can determine Z. Now we need to remember that a Z determined by using this equation is rounded off to the nearest integer number, which has to be splitted into a multiple of 2 and 3. Remember, whatever answer of Z came over here, we need to round it off in a integer term and also that in a multiples of 2 and 3. Okay, now let us proceed further. Third step, we need to find and list all the spindle speeds ranging from n minimum to n maximum. Now we know that the most suitable technique to distribute a speed is geometric progression technique, right? So n minimum would be given in the data, that would be our n1. Then n2, how we can determine n2? So n2 will be equal to n15, right? Then n3 will be equal to n25 up to n max. We need to list out all the spindle speeds. Okay. So this is our step number 3. Now step number 4, we need to decide number of stages, that is transmission group of a gearbox, which is denoted by capital N. Remember, number of stage is denoted by capital N. Now what is stage? What does this indicate? So as you can see on your screen, I have shown 2 diagrams. Let's see the first diagram. In this diagram you can see I have shown 2 shafts. On each shaft 2 gears are mounted. One is an input shaft, that is another one is a output shaft. So how much is the speed? How many speed steps we can obtain by this combination? So you would say 2 different speeds can be obtained. Okay. So this arrangement indicates that since there are 2 shafts used, so this is a one stage. Okay. This is indicating a one stage or a single stage. Okay. So in a single stage only we can obtain maximum up to 3 speeds. Okay, if we add one more gear over here, so maximum how much speed can we obtain? 3 speed. But we need a multi-speed gearbox, right? We need a 6 speed, we could need a 8 speed or a 12 speed or a 18 speed. So for that we need to increase the number of shafts. So as we increase the number of shafts, the stages are going to be increased. So to understand this in a better way, I have shown another diagram. You can see over here there are 3 shafts shown. Okay, so first and a second shaft you can see, let's say first is the input shaft, second is the intermediate shaft, and the third one is the output shaft. Now the power transmission takes place from an input shaft to the intermediate shaft. So this contributes a first stage, stage number 1. Okay, now maximum spindle speeds that could be transmitted would be 3, right? Now consider the intermediate shaft, that is a second shaft and a third shaft. So this represents a second stage. Okay, again over here the maximum speed steps available are 3. Okay, so total how many speed steps are available? So we would say 3 into 3, 9 speed steps are available in this entire gearbox arrangement. Now how 9 have came, so we are going to discuss that later on, but over here you need to clear that these 2 shaft where power transmission takes place represents one stage, then a next intermediate shaft, and an output shaft represents a second stage. Okay, so we need to determine that how many stage we required to design a gearbox. Okay, so how we can do that? So the equation over here, you can see I have written total number of spindle speed steps is given by Z is equal to number of speed steps in stage 1. So you can see this stage 1, in this number of speed steps are how many? So we would say 3. Okay, multiply by number of speed steps in a second stage. So in a second stage, how many speed steps we can obtain? So we would say again 3, because there are 3 gears and 3 speeds can be obtained. In this way, we can say that if a number of stages are increased, so we need to multiply by number of speed steps in a up to last stage. So generalized equation can be written as Z is equal to P1 into P2 up to Pn, where you can see I have written P1 is equal to number of speed steps in a first stage or a first transmission group. Similarly, P2 number of speed steps in a second transmission group. Pn indicates the number of speed steps in a nth stage of a nth transmission group. Okay, now where n indicates what? So n indicates total number of stages available in a gearbox. So our target is to find out this n. Okay, now let us proceed further. So in order to obtain the required speed steps, that is Z, our target over here would be to use a minimum number of gears. Remember, so using minimum number of gears, it is necessary that all the stages should have same number of speed steps. Okay, so we can say in a generalized equation, P1 is equal to P2, P2 is equal to P3, P3 is equal to P4, and so on up to Pn. Okay, so can I say that the previous equation, which was Z is equal to P1 into P2 into Pn, can be written as Z is equal to P into P into P. Why we are writing P into P into P? Because we are considering that in each stages the number of speed steps would be same. Now why we are considering this? So we need to obtain minimum number of gears. We need to design a gearbox in such a way that we are using a minimum number of gears, so that a compactness could be increased and we can obtain high speed steps. Okay, now can I write this equation in a further form? Z is equal to P raised to n, right? Now our target obviously is capital N, so we are going to apply log on both the sides. So from this equation, can I say directly we can find out a number of stage of a gearbox is given by capital N is equal to log Z to the base 10 upon log P to the base 10, where remember P would be either 2 or 3, as we have discussed that the number of speed steps in each stage has to be a multiple of 2 or 3. Okay, so it would be, we need to factorize whatever Z value is given in a data, we need to factorize it in terms of 2 and 3. Okay, now if the value of n obtained from above equation is not an integer number, okay, integer number means it is a fraction. So we need to, we would say that we need to modify this equation. So in following manner, so we can say that our generalized equation was what? Z is equal to P1 into P2 into P3 up to Pn, right? So we know that P1, P2 would be either 2 or 3. Okay, so we have modified this equation in another term. So you can see that Z is equal to 2 raised to n1 into 3 raised to n2. Okay, 2 raised to n1 into 3 raised to n2. So what these two indicate? That there are two speed steps available in a particular stage. Let's say in a stage n1. Okay. Then 3 indicates that there are 3 speed steps available in another stage. Let's say in stage 2. Okay. So the power indicates a number of stages. Remember, power indicates number of stages. So 2 raised to n1 into 3 raised to n2. Now, if the question comes that how much would be the total number of stages? So you would say that n would be equal to n1 plus n2. So this is the total number of stages in our multi-speed gear box. Let us understand this by taking a simple example. So you can see I have considered Z is equal to 12. Okay, which means that we have a gearbox having 12 different speeds. Okay, 12 speed steps. So can I factorize this 12 in terms of 2 and 3, in multiples of 2 and 3? So we would say yes, 2 into 2 into 3, right? Which means 2 raised to 2, 4 into 3, that 4 into 3 would be 12. So over here you can clearly see that 2 raised to 2 indicates that in this 12 speed gearbox there would be two such stages in which the number of speed steps would be 2, and this 3 raised to 1 indicates that there is one stage in which the number of speed step is 3. So we would say n1 is equal to 2 and n2 is equal to 1. The total number of speed steps are how much? So we would say 3 stages are there in a gear box, that is a 12 speed gearbox. Okay, now let us proceed further. Now from this equation we need to prepare a structural formula. So the next step, step number 5, would be to prepare structural formula and construct a corresponding structure diagram. Now what is structure formula? We are going to say that the maximum number of speed that can be obtained from a 2 shaft is 3, as we have discussed previously by seeing the example, by seeing the diagram, right? So if there are 2 shafts, the maximum speeds available are 3 different speeds. Hence it is necessary to use an intermediate shaft between input shaft and output shaft. The structural formula helps to determine the number of stages and required gear to obtain the desired speeds, which means by means of a structural formula we can determine number of stages and how many gears are required to obtain a desired speeds. Structural formula is the mathematical expression giving a distribution of a number of speed steps in each stage, along with that number of spindle speed steps by which two adjacent speed values of each stage are separated. So these two things are indicated by structural formula. Remember, the first is it is giving a distribution of number of speed steps in each stage, that is indicating P1 is a number of speed steps available in stage 1, P2 is a number of speed steps available in stage 2, P3 is a number of speed steps available in stage 3. Now along with that it also indicates something else. So there are x1, x2, x3. You can see on your screen I have written a structural formula. Z is equal to P1 x1 into P2 x2 up to Pn xn. So these x1, x2, x3 are the characteristics in a stage, indicating that number of spindle speed steps by which two adjacent speed values are separated. You will get a clear idea about x1, x2, x3 once we solve the numericals and E1 by seeing some examples. Okay, so let's proceed further. Now, as you can see, X indicates a number of spindle speed steps by which two adjacent speed values of a particular stage are separated for a first stage, for a second stage, up to nth stage. When we consider any two adjacent speeds available in this stage, if the difference between these two speeds is 1, then we would say X is equal to 1. So in a particular stage, if there are two different speeds, and the difference between the two speed steps is 1, then we would say x is equal to 1, which means difference between the adjacent speed value is 1, so we take x is equal to 1. Whereas if the value is 2, then we would take x is equal to 2. Thus for each stage there would be a particular value of x. So the value of x1, x2, x3 would be, always remember that for a first stage always x will be equal to 1. X1 will be equal to 1. Remember, okay, this is fixed. Every time in every structural formula, whenever you form, we need to remember that we are going to take x1 is equal to 1. Okay guys, now next, now what would be x2? What we need to take x2? So you are going to take x2 is equal to p1. Okay, now what would be x3? So x3 will be a multiply of p1 and p2. Okay, so x3 will be equal to p1 into p2, and so on. X4 is equal to p1 into p2 into p3. Okay guys, so I hope that you will get an idea. You are going to remember this. Okay, now for example, you can see on your screen I have written Z indicates number of speed steps available and capital N indicates number of stages. So if I ask a question that in a particular diagram how many stages are there, and second my question would be how many speed steps are available, so you would say that there are two shafts available, which means there would be one stage. Okay, power is transmitted from input shaft to output shaft. Now next question is how many speeds available, so you would say that there are two gears available. On each shaft there are two gears, which means the speed transmitted would be two different speeds between between these two shafts. Okay guys, so Z will be equal to 2 and N will be equal to 1. Now let's proceed further. Let us take another example. Now over here I have shown a multi-speed gearbox. Okay, and it is going to transmit 9 different speed, which means it is a 9-speed gearbox and there are 2 stages available. So the diagram is given. You need to determine that how many speed steps would be transmitted and how many stages are there. Okay, I have written the answer over here. You can clearly see. So let us see how we are going to predict. So if you see the second stage, there is a shaft 2 and shaft 3. Corresponding to that, there is a three gears. Okay, on shaft 2 there is a purple gears. You can see on shaft 3 there are pink gears. So can I say at a time one gear will be in meshing, so one speed. Now when I am going to shift to a second intermediate gear, so can I say a second speed will be available. And when I am going to shift to the third gear arrangement, can I say a third speed will be obtained. When it is in a stage 2. Okay, so in stage 2 how many different speeds? Three different speeds will be obtained. Now see the stage 1, which I have shown, that is input shaft and an intermediate shaft. On an input shaft there are green gears mounted. Similarly on an intermediate shaft there are 3 yellow gears mounted. Okay. When I am going to connect this first pair, okay, so can I say I am going to get a 3 different speeds of this stage 2. Okay, when I am going to connect this first pair. Now when I am going to shift this yellow gear in a second for meshing with a second arrangement or a second pair, can I say another 3 speeds will be obtained, right? So total how many speeds we have obtained? 6 different speeds have been obtained. Okay, by meshing the first pair I have obtained 3 different speeds from here. Okay, and by meshing the second pair of this stage 1 arrangement, another 3 speeds will be obtained by this gearing arrangement. So total how many speeds? You would say total 6 speeds. Okay, 6 different speeds. Now when I'm going to mesh the pair, that is a third pair, so can I say again a three different speeds will be obtained from a stage 2. So total how many different speeds are going to be obtained? So corresponding to each meshing, I am going to say 3 speeds are going to obtain. Means total how many speed? 9 speeds will be obtained. So how we can represent these 9 speeds? So we can say Z is equal to 9. So as we know our structural formula, Z is equal to 3 into 3. Okay, 3 into 3 indicating that 3 speed steps in stage 1 and 3 speed steps in stage 2, which is equal to 9. Now how many stages are there? So you would say that 3 raised to 1 into 3 raised to 1. So total n is 2. So over here you can see I have written P1 is equal to 3, P2 is equal to 3, where P1 is number of speed steps in stage 1, P2 is number of speed steps in stage 2. Okay, and P1 is equal to P2. So I hope guys that you are clear that how we are going to determine a structural formula and how we are going to predict it from a gearing diagram. Okay, now let's proceed further. So we are going to see a structural formula. Let us consider an example of a 4-speed gearbox in which Z is equal to 4. So breaking this equation, can I say we can write it as Z is equal to 2 into 2, indicating P1 is equal to 2 and P2 is equal to 2. Now how many stages would be there? So we would say 2 raised to 1 into 2 raised to 1. So 1 plus 1, the power, we are going to add the power. So number of stages would be how much? N is equal to 2. Okay, now let us see the combinations of a structural formula. So combination of P would be 2 into 2. Now also we need to consider a combination of X, that is a number of speed steps by which two adjacent speed values are separated. So we would say that there would be a two combination of X. One would be 2x1 into 2x2. Okay, so this x1 x2, and second combination would be 2x2 into 2x1. Okay, so over here you can see I have written two structural formulas. Z equals to 2 in a bracket x1 into 2 in a bracket x2, and second structural formula Z is equal to 2 in a bracket x2 into 2 in a bracket x1. So over here I have written Z is equal to 2 in a bracket 1 into 2 in a bracket 2. Now how this 2 has came? So we know that we need to take x2 is equal to p1. Remember, x2 is equal to p1, right, associated with x1. So our structural formula will become Z is equal to 2 1 into 2 2. Okay, SF2, that is second structural formula, Z is equal to 2x2 into 2x1. Okay, Now we know that we are also always going to take x1 is equal to 1. So x2 will be equal to 2 again in this. So equation will become z is equal to 2 in a bracket 2 into 2 in a bracket 1. So rule to select the best structural formula is that x should be in ascending order. Remember, x should be in ascending order, which it is going to follow in the first case. So you can see the value of x1 and x2 are in an ascending order, in an increasing order. So first is 1, second is 2. Okay, now of the different structural formula obtained, it should be noted that the following conditions should always be fulfilled to have a feasible kinematic solution. That is, z upon p into x must be an integer greater than or equal to 1. Okay, so you can clearly see that z is how much? So 4 upon p into x. So if you see the first structural formula, p into x, which means 2 into 1. Okay, so it is obviously it is greater than 1. Okay, similarly 2 into x2. So 2 into x2 is what? 4, right? So 4 upon 4 is what? 1. So it is equal to 1, which means this structural formula is feasible. Okay, similarly in a second structural formula case, this is going to be followed. Okay, it would be, this value would be greater than or equal to 1. But what is the rule? So x should be in ascending order. So because of that, we have selected SF1 as an optimum solution. Okay, now also we need to remember that a product a p into x must be a factor of z, and it should be less than or equal to z. It should not be greater than z. P into x, this value p into x should always be less than or equal to z. So you can clearly see in our first case also 2 into 1, which is less than 4, right? 2 into 2, which is equal to 4. So it is following this condition. So remember that while designing a structural formula, this condition has to be satisfied. Now let's proceed further. Now considering a 6-speed gearbox that is indicated by z is equal to 6, breaking this equation we would say in terms multiple of 2 and 3. So z is equal to 2 into 3, or we can say 3 into 2. So I am writing it as 3 into 2. So according to that, p1 is 3, p2 is 2. How many stages are there? So we would say there are 2 stages in this 6-speed gearbox. Okay, that is 3 raised to 1 and 2 raised to 1. So 1 plus 1 would be 2. Okay, now combinations. So possible combinations would be, can I say that in a for one case I can write 3 into 2. Now with 3 into 2 I can use two combinations of x. That is, I am going to take 3 in a bracket x1. Okay, you can see a first case 3 in a bracket x1 into 2 in a bracket x2. Similarly, by using this 3 into 2 combination, can I interchange the value of x? So that is going to become a second structural formula. So the second combination would be 3 in a bracket x2 into 2 in a bracket x1. Okay, similarly, can I interchange the combination of p? So we can even write 2 into 3, right? So when I'm going to take 2 into 3, so again the combination of x would come in picture. So 2 in a bracket x1, okay, into 3 in a bracket x2. So this is one combination. Okay, now similarly, can I interchange the value of x? So in a fourth case, can I say z is going to become equal to 2 in a bracket x2 into 3 in a bracket x1. So in every case, you can clearly see that first we need to arrange the p. Okay, that is a speed steps combination. So first 3 into 2. Okay, and accordingly by using 3 into 2, we are going to interchange the value of x. And similarly, by using 2 into 3, we are going to interchange the value of x. So by doing this, we are going to get 4 different combinations of a structural formula. So according to the first combination of structural formula SF1, we get z is equal to 3 in a bracket 1. So we know that always x1 will be equal to 1 and x2 will be equal to p1. Okay, so p1 is what in this equation? So 3, p1 is equal to 3. So I have written z is equal to 3 in a bracket 1 into 2 in a bracket 3. Similarly, SF2, you can see our combination is 3x2 into 2x1. So z is equal to 2 into 2 into 3 into 1. So x1 is 1 and x2 would be how much? So x2 would be equal to P2. Similarly, next structural formula SF3, we can say z is equal to 2 into 2x1 into 3x2. So in this case, can I say x1 is equal to 1 and x2 will be equal to P1. So equation will become z is equal to 2 in a bracket 1 into 3 in a bracket 2. Okay. Similarly, SF4, that is a combination z is equal to 2x2 3x1. So according to this, we can say x1 is always will be equal to 1. And what would be x2? So x2, we are going to take the value of p, which is corresponding to x1. So corresponding to x1, the value of p is what? So it is 3. So over here you can clearly see that I have written 2 3 into 3 1. But out of these four different combination, which is the best combination of a structural formula? So we would say our rule is x should be in a ascending order. Okay, and we would consider in this case SF1 and SF3, in which you can see that x is in a ascending order. X1 is 1, x2 is 3. Similarly, in structural formula 3, x is 1 and x1 is 1 and x2 is 2. Okay, so these two are the considered to be the optimum structural formula. Also, you can check that z upon p into x1 is satisfied in both these equations. That is, it is integer greater than or equal to 1, and similarly the product p into x would be less than or equal to z. So this is how we are going to determine the optimum structural formula. So first we are going to list out the different structural formulas which could be available for this particular speed. Okay, that is 6, and then after we are going to find out the optimum structural formula. Okay guys, so in today's session we are keeping up till here. In the next session we will continue with our design procedure of a multi-speed gearbox. So till then, stay tuned and thank you all.